Hi everybody, in the third lesson, nervous system, part 3 of your biology subject in the third secondary year LS section. In this presentation, we will take a look on the action potential. We will see some of its properties. Where can we record it? We will see that we can record it in many structures of the nervous system, and it has some properties that we have to learn. And we will start, as usually, by what we have to know before starting. We have to know the neuron. We are repeating now some information. The neuron with its parts. The parts of the neuron where we can study the nerve message is only the axon. The other parts usually are used in other ideas and other concepts. We will see them. Now the neuron and action potential we made before an explanation of the action potential, and we said that the action potential can be recorded inside a nerve fiber, as you see here. Now in this lesson, as I said, we will explain the intervention of myelin in it. And we made in some previous experiments a stimulation of the neuron, and we observe after the stimulation an action potential inside the fiber of it. This action potential can be recorded by inserting a positive electrode of a voltmeter or of an oscilloscope inside a nerve fiber, and by putting the negative electrode outside. This is how usually we record the action potential. And we will obtain on the oscilloscope, if we use an oscilloscope, this recording that is made up of a depolarization, repolarization, and here the figure misses a hyperpolarization. So what are the properties of the action potential? This experimental setup let us study some of the properties of the action potential. This is a neuron that is put in water, the physiological liquid of our bodies, as water and some ions in it. Now, this is a stimulator that permits us to stimulate the nerve fiber of this neuron, and this is a recording electrode that can help us to observe the variation of the potential. As you see here, when it is inserted inside, a potential difference of minus 60 millivolt is recorded on the oscilloscope. This is the resting potential, as we said before. And now the stimulation also can be recorded on this device in order to know how much is the stimulation strong. Now we can start by making a stimulation. These are two stimulations. They give us very slight variations. No action potentials were recorded. And when another higher stimulation is done, you can observe this stimulation is higher and it can't give me an action potential. But when it becomes higher, much higher, it leads to an action potential that arrives to plus 40 millivolt. This is the action potential that we are obtaining here. But what if we make more higher stimulation, as you see here? The action potential remains with the same amplitude as before. You can observe that even if we continue to increase the intensity of the stimulation on the fiber, you will not obtain a higher amplitude of the action potential that we are seeing here. The amplitude of the action potential remains constant. And this is a very important property of the action potential that we will study its origin further, but now we are interested only about the property. We saw in this previous experiment 2 results, and each of them can give us a property of the action potential. The first result is the action potential is obtained starting from a minimal intensity of stimulation. We saw that when the intensity of stimulation is very low, the action potential is not obtained. But when it becomes sufficiently high, we obtained an action potential. This leads us to the first property of the action potential. There is a stimulation that we call threshold. What does the threshold mean? Threshold means this minimum value of the intensity of stimulation, starting from which we can obtain action potential and below which action potential is not obtained. This is the threshold. The intensities that are higher than the threshold are called above threshold stimulation. The ones that are below the threshold are called below threshold stimulations. And the stimulation that is just equal to the threshold, and it is the minimal that is able to give you an action potential, is called the threshold stimulation. This result allows us to conclude this property. There is a stimulation threshold starting from which, so not any stimulation is able to give you an action potential. Starting from this stimulation threshold, you can obtain an action potential. This is the first property. We obtained also another result. The action potential keeps the same amplitude when the intensity of the stimulation increases above the threshold. And this allows you to take the other property, action potential obeys the law of all or none. What does it mean? What is this meaning? Action potential obeys the law of all or none means that either you can obtain all the amplitude of the action potential, not half, not quarter, not bigger. You can obtain all the amplitude of the action potential, or you obtain none of it, non-action potential, no action potential. This leads us to this result, leads us to this property. In other words, this property means that the action potential conserves its amplitude when we keep increasing the intensity of the stimulation above the threshold of stimulation. These are 2 properties of the action potential. Now we go to the next. Recording of an action potential in 2 points. This concept is not said before, is not explained before. This is the same action that we used before, and we can on it connect 2 oscilloscopes, not only one. This is the first, this is the second. This is the point where we connect the first oscilloscope at the beginning of it, and this is the point where we connect the second oscilloscope. Now we can observe, when we connect them, resting potentials on both of them, as you see here. And it is very obvious that we will observe resting potential since no stimulation is done, no action potentials are transmitted. If we make a stimulation of the neuron, now we will observe an action potential. But where will be obtained? Where it will be obtained? You can think now. You can think. Will I obtain action potential near to the stimulation only? Will I obtain an action potential far of the stimulation only? Or I can obtain action potential in both of them? Is the action potential able to go from this point and to reach the next point? Or it is done always near to the stimulation and I need many stimulations to make the action potential pass to the other point? Let's see. This is the stimulation. It leads to an action potential in the first, and it leads also to an action potential in the other. So, observe it carefully. This stimulation allows us to observe an action potential here with this latency time, the time needed for the action potential to begin. And this is the other point where I have higher latency time. I need to wait more to obtain an action potential. What does it mean? Please think about it. What does it mean? What properties can you take? What properties can be taken from this very simple experiment? Don't forget also to think about the amplitude of the action potential. Look at the amplitude. Do you observe it? This amplitude at the beginning, and this is the amplitude where at the end, without saying now the values. Let's see. We have also a result and a property. The first result, the action potential is obtained at the beginning and at the end of the nerve fiber. What does it mean? It means like the action potential obtained at the beginning can pass to the end. So the action potential propagates. This is the first property that we can take from this experiment. Action potential can propagate within the nerve fiber. Now, the second result, action potential has the same amplitude at the beginning and at the end of the fiber. Don't mix this idea with the first one, where the action potential has the same amplitude when we increase the intensity of the stimulation. Here, I didn't increase the intensity of the stimulation. The intensity of the stimulation is one stimulation, not many stimulations. But this one stimulation makes us obtain an action potential at the beginning of the fiber and at the end of the fiber. This makes us conclude that the action potential propagates, but the amplitude obtained at the beginning is the same as the amplitude obtained at the end. So this is the second property. Action potential keeps the same amplitude while propagating. I'm not saying here that it keeps the same amplitude while increasing the intensity of the stimulation. This is another property. The same amplitude is kept while propagating. So when the action potential propagates inside the fiber, it keeps its amplitude constant. Now we obtained 4 properties of the action potential. It has a threshold. It keeps its amplitude when we increase the intensity of the stimulation above the threshold. It propagates, and it keeps its amplitude constant while propagating inside the nerve fiber. These are the 4 properties that we can take from this experiment, and you can think more about some other properties that are hidden inside the properties that I noticed. Action potential can make you think about the nerve fiber. The nerve fiber itself is excitable, so it can make activity when it is stimulated, and it is conductible since it can make the action potential propagate inside of it. These are the properties of the nerve fiber, and that I'm now telling you about them since they are related to our subject of the properties of the action potential. Now, another property of the action potential is its speed. How can we calculate the speed? The speed of the action potential can be calculated by using this device. This is an oscilloscope, and this is another oscilloscope. On the oscilloscope, you can observe a scale of 0.5 millisecond for each division. This scale, for the first time, lets you calculate the time needed for the action potential to happen or to propagate. The first and the second oscilloscopes are connected to 2 different points, and a stimulation is done, and it leads to what? It leads to 2 action potentials. You can see here that the first electrode has a distance between it and the stimulation site. And this distance from this point to that point is crossed by the action potential when the time passes from this point, which is the point where the stimulation is done, is the time where the stimulation is done, to this point where the action potential reaches the recording electrode. So this is the time needed for this distance to be passed by the action potential. If you have the distance and the time, what can you calculate? You can calculate the speed. Another oscilloscope allows us to calculate also the same speed. This is the distance that the action potential pass in it, and this is the time needed. If you have the distance and the time, you can also calculate the speed. In another third way, you can calculate the difference of time needed for the action potential to pass from the first oscilloscope to the second, here, from here to here. And the distance between them, you have this distance, and this distance take this time to be passed by the action potential, this time. So you have three ways to calculate the action potential if you have two oscilloscopes. You can calculate it from the distance of the first oscilloscope and its time, the distance of the second oscilloscope and its time, or the distance between the two oscilloscopes and the difference of time between them. For the three cases, you can use this formula, V equal D over T. D is measured by centimeter. You can take it by meter. And this time is measured by millisecond, and you can take it by second by converting them in order to obtain the speed. We will make some exercises about the calculation of the speed further after this lesson. Now, can we speed up our nervous messages? If it is so, we will be fast. We will be faster. We will think faster. We will make our stuff faster. But is it possible to increase our speed? This speed that we calculated now, can we speed it up? What do we know? What do we have to know in order to answer this question? I want you to think, what do we have to know if we want to know if we are able to speed up our nervous messages? I will tell you. We have to know the conditions that affect the speed of the nervous message. What are these conditions? Let's see. This table is taken from your book. Your book shows you many fibers, and for each of them, the average diameter of nerve fiber that is put here, and gives you the average speed of propagation that is not the same. This is the variable factor that leads to these results. And we have another variable factor, which is the myelin. We have 3 myelinated fibers, plus means presence. And we have these 2 fibers that do not have myelin, minus means absence. And this is a little bit complicated question when we give you a given. And in the given, you have more than one variable factor, and we ask you to interpret the results shown in the table. If we ask you so, you have in your mind to differentiate between the variables in order to answer. Here I have the first variable, which is the diameter, and I have to study it in the first case and in the second case. This is the first variable. And by comparing between the two cases, we are taking into consideration the next variable, which is the myelin sheath that are surrounding the nerve fibers, and that we have spoken about in some slides before, in some previous slides. For this question, how can I make an interpretation? I have to, and I will show you the answer in a few seconds. The fibers here, the fiber has high diameter, this fiber has low diameter. If you compare the speed, you will notice that this speed is higher than this one. So the increase of the diameter makes the action potential faster. This is a very important property. For the myelinated fiber, as for the non-myelinated fiber, when you increase the diameter, you will obtain higher speed. And this is applicable for both kinds of fibers. When the diameter of the nerve fiber increases, the speed of the nerve message becomes faster. It means that the increase of the diameter speeds up the nerve message. For the fiber that doesn't have myelin, a very high diameter let the message with a speed lower than a fiber with myelin, even if the diameter is less. Let me show you. In the presence of myelin, and this is the analysis, the fiber of big diameter equal to 13 micrometers has an average speed of 75 meters per second. This speed becomes less in the fibers of lower diameter to reach 11 meters per second, in the fiber of average diameter equal to 3 micrometers, as we see here. Similarly, in the absence of myelin, the fiber of big diameter equal to 700 micrometers has an average speed of 25 meters per second. This speed becomes less in the fiber of lower diameter having 1 meter per second, in the fiber of average diameter equal to 0.5 micrometer. This leads us to this meaning. This means that the increase of diameter of the nerve fiber speeds up the propagation of the nervous message. This is the first meaning taken from this given. If we take this given again, according to the myelination, the presence or the absence of myelin, you can read this analysis. In the absence of myelin, the fiber that has bigger diameter of 700 micrometers has a speed of propagation of 25 meters per second. That is much less from the speed of the fiber having less diameter of 13 micrometers. That is obtained where in presence of myelin, where the speed is 75 meters per second. What does this lead us to conclude? This means that the myelin speeds up the propagation of the nervous message. So what are the conditions of that speed up the propagation of the nerve message? They are the myelin and the diameter of the nerve fiber. But since these two conditions are not under our control, so we can't speed up our messages. We can't speed up our nervous messages by simple varying these conditions. And these are not the conditions that we can change. There is a third condition that can change the speed, which is the temperature. But since our body temperature is also stable, it is also constant, so we can't also use this condition to speed up the nerve message propagation. The propagation in the myelinated fibers is higher, is faster than propagation in the non-myelinated fiber. This is what we have seen. Why? Since the propagation, when the propagation is done, the charges are inverted. And the inversion of the charges leads to the inversion of the charges in the next point, just next near to it, in the non-myelinated fiber. This leads to the action potential to pass point by point. And since it passes point by point, it will be very slow. But in this case, if the action potential is done in the myelinated fiber in this point, since the myelin isolates the nerve fiber, so the action potential can't be done in each point by itself. It can't pass point by point. It passes directly from this site that is called Ranvier node and it passes directly to the next Ranvier node. So the action potential in the case of myelinated fibers jumps from one Ranvier node to the next, from one Ranvier node to the next by the same mechanism that is responsible for the propagation in the non-myelinated. The mechanism is the same. This positive charge attracts the negative charge and leads to the opening of the Na plus channels in this site, leading to an action potential in it. Now, the positive charge attracts these negative charges and leads to the opening of the Na plus channels, voltage-dependent Na plus channels at this site, leading to the new action potential at this point. The same mechanism is done in both, but it is much faster in the second, since they are isolation of the fiber by myelin, and the prevention of the action potential to taking place, to be happening where inside the myelin it happens only between the two myelin sheaths that is called Ranvier nodes, that are called Ranvier nodes, and this is why the action potential is faster in the presence of myelin than in its absence. Finally, in this lesson, we have to understand other properties of the action potential, but not in the nerve fiber. I already said that we have to study the properties of the action potential in many structures. The first structure that we studied the action potential properties in it is the nerve fiber. Now we will study the properties of the action potential were in a nerve, not in a nerve fiber. I have to remember you that the nerve is a group of nerve fibers where the nerve fibers go from the central nervous system, the nerve centers, to the body parts. They are connected to the body parts in bundles of fibers that make the nerve. If we make a stimulation of the nerve, we can notice that with the very low stimulations, we will not observe any action potential. And this is very normal, since if one fiber can't make action potential, so the whole fibers grouped together, can't make action potential for low stimulations. This stimulation is the first and the minimal stimulation that leads to the action potential. What do you call this minimal stimulation able to make an action potential? We call it threshold, stimulation threshold. And what do we call these stimulations? We call them below threshold stimulations. All these stimulations that are higher than this one are called what? They are called above threshold stimulations. And it's obvious that these stimulations will give us action potentials. But what properties? The first property of the nerve is same as the first property of the fiber. The nerve has a threshold stimulation intensity. But if we increase the intensity of the stimulation in the nerve, does the action potential that is called here global potential, does it conserve its amplitude? Observe. It doesn't conserve its amplitude. It increases in amplitude. Why? Why will a nerve increase in amplitude while a nerve fiber remains constant? Why? Since when we increase the intensity of the stimulation, the number of fibers that are making action potentials becomes higher. And when the number becomes higher, more fibers making action potentials will give you a higher global, a higher sum of the action potentials. And this is why we say that the nerve obeys the law of summation, not the law of all or none. We can't observe all or none. We observe some or many intermediate states of the action potential that make us say that the action potential called global potential inside the nerve obeys the law of summation, not the law of all or none. What will happen if we increase more the intensity of the stimulation? You can observe here how the amplitude of the action potential of the global potential remains constant. Why? Since simply all the fibers are excited, so I can't increase more the amplitude of the action potential, because all the fibers that are making this action potential appear become maximal and constant, and I will not obtain any increase of the amplitude again. These are the properties of the nerve that are a little bit, and some of them similar to that of the fiber, and some of them are different. So let's repeat again in very few words. The fiber has 4 properties. It has a stimulation threshold. It conserves the amplitude when we increase the intensity of the stimulation above the threshold. 3, it conserves, it propagates, the action potential propagates inside the fiber, and it conserves its amplitude while it propagates. It has a speed. This speed is becoming higher in the presence of myelin. It is becoming higher in the fibers with bigger diameter, and we have learned how to calculate this speed. And for the nerve, it shares some properties with the fiber, since the nerve is a group of fibers. It has a threshold. This is the threshold, but it increases in amplitude when the intensity of stimulation increases, but it reaches a maximum since the number of excited fibers increases with the increase of the intensity of stimulation, and when all the fibers are excited, I will obtain a constant amplitude at the end of the experiment.